and the connection between MCSP and cryptographic primitive called obfuscation. This is based on two works, one work with Rafael and one work with Gergen, Igor, and Rafael. What we are going to see is two results. The first is that the existence of a cryptographic primitive called obfuscation implies a barrier on proving the NP-completeness of meta complexity problems. So again, a connection between cryptography and meta complexity. And the second result will be to look on this connection from the other direction in order to show that if we know that problems in meta complexity are NP-complete, we can get lower bound on cryptography, on the existence of obfuscation. So let me start with the definition of the minimal circuit size problem, or MCSP. So in this problem, we get as input a string of length m, and we think about the string as a truth table of a function. So a function from log n bits to 1 bit. And the question is, what is the minimal size of a circuit that computes the function described by this truth table? So for example, if we get this truth table, it can be represented by the string 0, 1, 1, 1. And we ask what is the minimal circuit that computes this function. In this case, it's not hard to see that this function is the O function, so the answer is 1. And we also can define a gap version of this problem, in which we have two parameters, S and L, when S is small and L is large. And we get as input string T, and we need to distinguish between two cases. The yes case in which there is a small circuit that computes the function described by T, and the no case in which there is no large circuit that computes this function. So in the yes case, there is a circuit of size S that computes T. In the no case, there is no circuit of size L that computes. And it's not hard to see that this problem is in NP. The input for this problem is the truth table of the function, and the witness is the small circuit that computes this function. And since the input is the truth table, we are allowed to run in polynomial time in the truth table, so we can just evaluate the circuit on every possible input and check that it computes the right function. So now we have the definition of GapMCSP. And a natural question is, this problem is in NP, so to understand how hard it is. And what we know is that assuming cryptography, this problem is actually hard. So if we have a function, GapMCSP for any polynomial gap is hard to compute. And moreover, if we have obfuscation, a strongly cryptographic primitive, then the hardness of GapMCSP is roughly equivalent to the hardness of NP. So if we know that GapMCSP is in BPP, we know that the entire NP is in BPP. But so we have evidence that this problem is hard. The next question we can ask is this problem is NP or NP complete? And here we do not know that. So we do not know if GapMCSP is NP complete. There are variants of these problems that we do know that are NP complete, or other meta complexity problems that we do know that are NP complete. Multi-MCSP that I will talk more about, MCSP star, in which we get a truth table, in which for some of the entries, we don't care what the value is. This one, we know that it's NPR, and Raul has a work that showed that MCSP with access to a random oracle is also NP complete, but we do not know if GapMCSP itself is NP complete. We have barriers on proving NP completeness of these problems, and what I want to show you today is a specific barrier, a barrier on proving the NP completeness of this problem with respect to so-called level reduction. So the next thing I want to say is what are level reduction.
So, are you have a promise version of GapMCSP, or just something you're just talking about anything that solves when the gap conditions met?
Sorry?
Are you have a promise version of the problem?
I'm not talking about the promise. Or large enough gap.
So you're just saying that if you have an algorithm that solves GapMCSP, you can do anything on the middle. but it does have to, okay, it doesn't get the promise that there is no middle. Okay.
Yeah.
Okay. Perfect.
Okay, so the usual way we define NP-completeness is with respect to polytime reductions or many-to-one reductions or CARP reduction. So if you want to prove that GapMCSP is NP-complete, we need to show a CARP reduction from SAT to GapMCSP. And a CARP reduction is an efficiently computable function that takes an input for SAT, SAT formula, and output an input for GapMCSP, a truth table of a function. And what we want from this function is that the formula phi will be satisfiable if and only if there is a small circuit that computes the truth table, this function described like this. So in other words, we want to say that if there exists a witness for this formula phi, if there exists a satisfying assignment for phi, then there exists a small circuit smaller than S that computes the function described by T. And in the other direction, if there is no satisfying assignment for phi, then there is no circuit smaller than L that computes the truth table. In other words, if there exists a circuit smaller than L that computes the truth table, then we have satisfiable assignment for this formula. So this is CARP reduction, and this is the correctness proof of CARP reductions. And Levin reductions are CARP reductions with constructive proof. So a Levin reduction is a triplet of functions, f, g, and g prime, where f is the CARP reduction, and g and g prime are the constructive proof of correctness. So g is a function that takes a witness for phi and output a small circuit that computes the function, and g prime is a function that takes a small circuit that computes this function and output a satisfying assignment for. So these are Levin reductions. And this way, if you think about this, is the natural way to prove the correctness of a reduction. So almost all the reductions that we know are Levin reductions, including the PCP theorem. The proof of the PCP theorem is constructive, so it's also CARP reductions. And also this property that we can take witness for instance, for SAT and transfer it into a witness of GapMCSP is useful for applications. So we also need reductions to be Levin in order to use them for applications. And what we showed in this work is that under cryptographic assumptions and for large enough gap, the GapMCSP problem is actually not NP-complete with respect to this type of reduction. And we have a similar result for time-bounded Kolmogorov complexity, or the Gap version of time-bounded Kolmogorov complexity, and for randomized non-uniform sub-exponential Levin reductions, so a larger class of reductions, inefficient reductions. What are the cryptographic assumptions? So we need two assumptions. The first is a mild assumption. I will say what it is later, but basically this is one function. The second assumption is more strong, is what we call indistinguishability obfuscation. And this is a very strong cryptographic primitive. It basically allows us to take circuits that compute some function and to construct from it a new circuit that computes the same function as the original circuit, but hides the internal implementation of the original circuit. And this is a very strong cryptographic assumption. Till recently, we didn't know if this primitive is actually exists, but now we know that how to construct this primitive based on well-studied assumption. And anyway, I'm going to use this assumption in order to prove a lower bound. So unless you will prove that obfuscation do not exist, you will not be able to prove that GapMCSP is definitely complete. So let me define what is obfuscation more formally. Indistinguishability obfuscation is an efficient function, randomized function IO, that takes a circuit and output an equivalent circuits that compute the same functionality. But for every two equivalent circuits, C1 and C2, that computes the same function and has the same size, we cannot distinguish between the obfuscation of C1 to the obfuscation of C2. So the IO hides the internal implementation of the circuit. We cannot know what was the original implementation. And as I said, this is a very strong cryptographic primitive, and we know how to construct strong cryptographic primitives from it. So we know that if we have IO together with the assumption that NP is out, it's not in BPP, then we can construct finite functions, public key encryptions, multi-party computation. Basically, all cryptography can be constructed from IO together with a minimal analysis. Now, the picture here is a bit misleading in the sense that the IO takes a circuit, but maybe it outputs a larger circuit. And this is the overhead of the IO. It's like maybe a small circuit and output a larger circuit. So the overhead is the relations between the size of the output of the IO to the input. And this is at most a polynomial always because the IO is an efficient algorithm. So what we showed in this result is that if we have obfuscation with overhead P, with some polynomial overhead, then GapMCSP with the same gap, when the gap is the overhead of the IO, is not Levin epical. Okay, so this is the result. So let me show you the idea behind the code. And I will say what the assumption that we are going to make. So the first assumption that I'm going to make just for this talk is that the half reduction between SAT to GapMCSP is not too shrinking. The output of the reduction is polynomially related to its input. Otherwise, we need a slightly more strong assumption. And then we need obfuscation. And we need a second assumption, which is collision-resistant hash function. And collision-resistant hash function is an efficiently computable function H from a small number of bits to from a large number of bits to a small number of bits. So there are many collisions in this function, but any efficient algorithm cannot find any collision, cannot find any single collision. Okay, so there are many collisions, but we cannot find them. And this is the second assumption. Now the proof that I'm going to show you actually do not need collision-resistant hash function. It's enough to assume target collision-resistant hash or universal one-way hash functions that can be constructed from one-way functions. The only reason that I defined collision-resistant hash function is that it's more known. It's easier to define. And as I said before, if we have obfuscation and together with the assumption that NP is not in BPP, then we have boundary functions, and then we have target collision-resistant hash functions. So this assumption can actually be replaced with the assumption that NP is not in BPP, which is actually a minimal assumption. And this is assuming that the reduction is right. And the idea of the proof is to use the Levin reduction and together with the IO in order to find a collision in the collision-resistant hash function. So to break the security of the collision-resistant hash. So let me show you how we do it. This is going to be pretty simple.
Sorry, I understood your question. So I guess I should think maybe the idea just clarified it, but in this definition, you're including randomized algorithm. So any efficient randomized algorithm cannot.
Yeah, of course. Yeah.
And so that's why the idea sort of makes it work.
Yeah. Okay, so we want to find collision. So we start with a Levin reduction and CRH, a collision-resistant hash function. We want to use the Levin reduction in order to break the CRH. And the first thing we are going to do is to define a SAT formula. So for every string y in the image of the CRH, we define py, which is a SAT formula that is satisfiable on a string x prime, if and only if age of x prime is equal to y. So this formula basically simulates the efficient function age, and then check if the output of the hash function is equal to y. And then to find the collision, we are going to sample a random string x, compute its output under the CRL, so compute y, which is age of x, and then apply the Levin reduction on the formula phi, verify y is the output of age. So we started from phi, we applied the Levin reduction, and we got a truth table, an input for GapMCSP, a truth table of a function. Now, from the way I construct the formula phi, I know that this formula is a SAT instance, is satisfiable. because I have a witness such that I know that phi on x is true. So I have a witness that satisfies phi. And now I can use the Levin reduction in order to use x to construct a witness for GapMCSP. So I get a small circuit that computes the truth table, the function described by truth. Now I have a circuit, so I can use the I/O to get a new circuit that computes the same function. And because the overhead of the I/O is not too large, the size of C prime is still not too large. So I still have a small circuit that computes the same function. Now I can use the Levin reduction again to get back a witness for phi x prime. And that's it. So now, just by the correctness of the Levin reduction and the way I construct the formula, I know that edge of x is equal to edge of x prime is equal to 1, because x prime satisfies the formula of phi. To say that this is a collision, I need to claim that x prime is not equal to x. And this is going to be by the security of the I/O. So let me show you why x prime is different than x. So the idea is to start with a collision with x1 and x2 that are different, and edge of x1 is equal to edge of x2. And to imagine that we do this experiment twice, once from x1 and the second time from x2. And now, since edge of x1 is equal to edge of x2, py is the same in both cases. And this means that the truth table that we get is the same in both experiments. And this implies that C1 and C2 are two circuits that compute the same function. So by the security of the I/O, we cannot distinguish between C1 prime to C2 prime. And this means, because age is an efficient function, that we cannot distinguish between x1 prime to x2 prime. And now, if we cannot distinguish between x1 prime to x2 prime, it must be the case that either x1 prime is different from x1 or x2 prime is different from x2. Otherwise, we can't distinguish. This means that when we choose a random input uniformly at random, at least with probability R, we must be able to find a collision and break the security of the I. Okay, this is the example. Good. So we have this result, and the same proof actually works when the reduction is randomized. If the I/O is secure against sub-exponential algorithm, this excludes reduction with sub-exponential running time. So depending on the security, we assume we get stronger results. And if we want to prove the same result for the gap version of time-bounded Kolmogorov complexity, we need to assume I/O for Turing machines, so randomize encoding. So we can choose the cryptographic primitive in order to have results for other meta-complexity problems. And the last thing I want to say about this result is that this gives us a connection between cryptography, between obfuscation to GapMCSP. And we can take this connection and look on it from the other direction. And if you look on it from the other direction, we get that if we will be able to prove that GapMCSP is Levin NP-complete, then we will get that obfuscation do not exist. So this gives us a way to prove that there is no obfuscation. It will be amazing. And of course, I'm lying here. If we will prove that GapMCSP is Levin NP-complete with a small gap, we will get that there is no obfuscation with a small overhead. So the overhead depends on the gap. But if we will prove that GapMCSP is Levin NP-complete for any polynomial gap, then we will get that there is no obfuscation. And of course, we do not know if GapMCSP is NP-complete. We do not know if it's Levin NP-complete. But we have other meta-complexity problems that we know that they are NP. And for example, we know that by the work of Ilan, Goluf, and Oliveira, we know that multi-MCSP, a problem that I will define later, is actually Levin NP-complete. And it turns out that if you look on this proof that I just showed you, the same proof works also for multi-MCSP. And as a result, combining these two results together, we get a first lower bound on the overhead of obfuscation. So we get that unless NP is easy, there is no obfuscation for circuits from n bits to n bits with a very small overhead. And the output of the I/O is the size of the original circuit plus something small. So this, next I want to talk about this result.
Just a comment, so your first corollary, it's not the star reduction that Yanni was talking about. You don't need to have the same reduction that gives you any gap, every gap.
No.
For a given gap, it's enough to have a reduction for that gap.
Yeah. For every gap, you get that there is no obfuscation with this gap, and if you will show it for any point of time,
Yeah.
How small is this overhead? And then, like, what are the overheads for non-IO instructions?
Yeah, so we don't have anything better than polynomial. If you care, so we care about the overhead as a circuit size, and there is a literature about the overhead in the description length of the output circuit, and then there is a small overhead, but when we look about the circuit size, we don't know anything. Not trivial. Okay. Okay. So we have this result. I just want to say that assuming that NP is in VPP, then there exists an IO with no overhead at all. There is a way to canonical the circuit and get an IO without an overhead. So there is an equivalent between NP and VPP and IO with small overhead. And also there is like a bootstrapping result. If you construct an IO with overhead smaller than this, you get an IO without overhead at all. Okay. So what I just said is that if you will put, by taking a result that multi-MCSP is definitely NP-complete, we get that there is no rate one obfuscation, there is no obfuscation with very low overhead. You can also look on other meta-complexity problems and get impossibility results on other types of obfuscation. So for example, if we look on the NP-completeness of conditional Kolmogorov complexity, we get that there is no obfuscation for databases with circuits with Oracle access to a database. You cannot obfuscate that in the sense that the overhead cannot be independent from the size of the database. And another result that we didn't check the details, but there are works that showing that DNF-MCSP is NP-complete. DNF-MCSP is the DNF version of the minimal circuit size problem. So you get a truth table and you ask what is the minimal DNF size of formula that computes this function. And this gives us, if we will prove that this is definitely NP-complete, it gives us a lower bound on proper obfuscation. So proper obfuscation for DNF formula is an obfuscation that takes DNF formula and output a new DNF formula that has the original circuit. And the reason I mentioned it is because I wanted to say something which is related to learning. And Boyle et al. Has a work that there is no proper obfuscation for CNF or DNF formulas with constant degree. And the way they prove it is with a connection to learnability of DNF formula. So I don't know, but maybe there is an interesting connection here between these two results.
So the last hand side is correct, so it was Lehman reduction?
So I'm not sure that this is, that there is a Levin reduction. I'm not sure what the parameters are. Okay, so let me define multi-MCSP. So in multi-MCSP, we get a truth table of a function, but this time instead from log n bits to 1 bit, from log n bits to m bits. So the size of the truth table is n by m, and we ask what is the minimal size of a circuit that computes this function. And again, we can define a gap version of this problem in which we have two parameters S and L, and we ask if there is a small circuit smaller than S that computes this truth table, or there is no circuit of size L that computes this truth table. And again, this problem is an NP, but this time we know that it's NP complete under Levin reduction, where the gap is S and S plus S over log S, which is the overhead of the IO. So this is the NP completeness of this result, and then we get this theorem, and the proof of this theorem actually gives us a distribution over circuit that we cannot obfuscate with lower overhead. And we can try to look on the proof and to understand how these circuits look like. But in order to do so, the proof that I showed you starts from using the IO plus the assumption that NP is not in BPP in order to construct hash function H. And then it uses this H in order to construct this formula Py. It uses the code of H inside it. And then it uses the Levin reduction from SAT to GapMCSP on the formula Py. And the Levin reduction from SAT to GapMCSP actually uses itself the PCP theorem and another chain of reduction. So the proof, the construction of the circle is pretty complicated. So what I want to show you now is a more direct proof of this result with worse parameters. So I will actually construct circuits that we cannot obfuscate them. And this is like a cryptographic result. There is not much meta complexity in it, but the ideas that we are going to use in the proof are actually inspired by works in meta complexity. So I think it's going to be, it's nice to see.
Shows.
No. This is not.
That's not your computer.
Both of those options seem very dangerous. Oh,
Yes. Okay. So to construct the circuits, we need to use pseudo-random functions. And pseudo-random functions is a family of functions indexed by a secret key K. And the security guarantee of this family is that we cannot distinguish between a random function from this family to a totally random function. So an efficient algorithm cannot distinguish between getting an oracle access to a function in the family to getting oracle access to a totally random. And we know how to construct pseudo-random functions from 1A functions. They look like random functions, but they actually can be computed using a very small circuit, a circuit of size polynomial in the internet. So now, using pseudo-random functions, we can construct a family of functions and circuits such that the circuits cannot be obfuscated using low overhead obfuscation. And the idea is first define the function that the circuits compute. So the idea is to use the PRF, and we are going to construct a function that takes log n bits and output n+1 bits, which are concatenates of n+1 function, such that the last function t is just going to be a random function from log n bits to 1 bit. And all the other functions are going to be computed as follows. So we are going to sample for each index I a random key for the PRF. And then we are going to define Ti to be the XOR between the output of T on an input X to the output of the pseudo-random function on an input X. So, and then we are going to take m such functions and concatenate them. So this is the function. And now we can construct circuits that compute this function. So the way we construct this circuit, I'm going to define m circuits that computes this function, one for each index between 1 to n, where the circuit Ci is going to be constructed as follows. So first, for each function T1, T2 to Tn, I'm going to construct a separate circuit that computes this function. And this is just going to be the trivial circuit of size m, the size of the truth table of the function, that computes this function. I'm not doing anything smart. And I'm going to do it for each one of the M functions. And then the last function T, instead of constructing a circuit that computes T, I can just construct a circuit that computes f of ki, and I know that there is a small circuit that computes it because this is a pseudo-random function, and then compute the XOR between the output of Ti to the output of M. And this gives us the output. So this is the construction of Ti. And of course, here I use the ith function in order to compute T, but I could use any other function. I could use Tj in order to compute. And the size of this circuit that I construct is I need a circuit of size roughly n for each one of the truth tables. This is the trivial size of the circuit, so n times n, plus something small in order to compute the output of Ti. This is the construction. And now what I want to say is that if I apply the obfuscation on Ci or on Cj, the security of guarantee of the obfuscation needs to promise that I cannot distinguish between Ci and Cj. But I'm going to show you that if the obfuscation has low overhead, then I can actually distinguish. This is not going to work, but this is what I want to know. So let's start with some assumption to make the proof easier. And let's assume that our obfuscation take the circuit Ci and always output the circuit T1 to Tn, to Tm here. And then it outputs some other circuit that compute T from this circuit. And the goal of the obfuscation is only to hide the index I from which I used in order to compute the function T. So it always outputs the original M circuit and then obfuscated only the last circuit that computes. Okay? And in this case, the claim is that if the new circuit that computes Tx is small, then it must touch a large fraction of the function T1 to Tm. And there are many functions that these circuits need to touch on, so it must be that the size of this circuit is large. Otherwise, it cannot touch many functions. So why this claim is true, why these circuits need to touch many of these functions? So the observation is that any small circuits that compute T of x must touch at least one of the functions T1 to Tm, because T is just a random function. So there is no small circuit that computes T. But if there is a small circuit that computes T, it must use one of the other functions that we have. But by the security guarantee of the PRF, all of these functions look random. They are indistinguishable from random, even if you know T of x. Now, the IO gets its input Ci. So he knows how to compute T from Ti. So if this circuit touches Ti, then it can be that it computes T with a small circuit because it got Ti as an input. But all the other functions looks like random function for the IO. It doesn't get any information about this function except for the truth table that computes this function. So it means that the IO of Ci, this circuit must touch Ti. It cannot use any other circuit in order to compute T of x. But if we apply the IO on Cj, then the IO of Cj from the same argument must touch Tj. So if you cannot distinguish between the output of the IO on Ci and the output of the IO of Cj, it must be the case that the output of the IO on Ci touches Tj also. And if the IO of Tj of Ci touch Tj also, it means that it actually touch every J, because there is nothing special about Tj. This argument works for any J. So it means that actually this circuit must touches all of these circuits. So if the size of the original circuit is n times n plus something small, the size of the I/O of Ci is n plus times m, because we need n times m in order to compute all of these circuits, plus n, because these circuits need to touch every one of these. And if we take, so the size of the output of the I/O is the size of the original circuit plus order of n. So now if we take n and m to be the same, we get that the overhead of the I/O is the size of the original circuit plus square root of the original circuit. So we prove the law on the overhead of the I/O. Of course, we had an assumption that we need to get rid of. Okay. So we want to get rid of this assumption that the I/O always outputs the original circuit and only change this part. And this result as is already give us a lower bound on some conditional version of obfuscation that we only want to obfuscate part of the circuit, but we want to get rid of the assumption. And it turns out that we can do it using ideas from the work of Ilan, Goluf, and Oliveira that proves the NP-Completeness of multi-MCSP. And what we really want here is to claim that this is always the case. For any obfuscation, we can always extract the circuit that computes T1 to Tm from the output of the I/O. So what we want is some kind of chain rule for circuit complexity. We want to claim that for any two functions f and g, if we want to look on the circuit complexity, the size of the minimal circuit that computes the concatenation of g and f, the size of this circuit is always the size of the circuit computing g of x alone, plus the size of the circuit computing f of x given the output of g of x. In other words, if I have a circuit that computes both g of x and f of x, I can break this circuit into two parts. One part that computes g of x, and the second part, given g of x and x, computes f of x. And I want that the sum of these two, the sizes of these two circuits, will be the size of the original circuit. This is what I want. And then I will be able to apply this chain rule on the functions g of x, which is just the concatenation of T1 to Tm, and f of x, which is just T. And this will give me the. But of course, this is not generally true. This is not true that we have a chain rule for circuit complexity. But it turns out that we don't really need chain rule for circuit complexity. We need something weaker that I'm calling here a pseudo chain rule for circuit complexity, because it reminds me the proof of all, the idea of pseudo symmetry of information. So what we actually need is an encoding of G, GR, or to prove that for every G there is an encoding of G, GR, such that computing G of X from GR out of X is easy, and the chain rule works for GR. This will be enough. And it turns out that there is such an encoding. We can do it for circuit complexity. And the way it was done by Ilan, Goluf, and Oliveira is as follows. So to encode a function g, we first construct some circuit C that computes g of x. So a canonical circuit that computes C of x. And then we take the circuit and make any internal gate of the circuit an output gate. And the encoding is going to be the concatenation of the outputs of all the internal gates. And now the idea is that I will call this circuit CR. And then the idea is that if we have small circuits that compute GR, or any circuit that compute GR, we can find a copy of CR, this original circuit, inside of it. Because given a function that computes GR, we can identify for any internal gate, for any output gate of G hat, which internal gate of C hat it computes, and then we can just rewire the circuit according to the wiring of C hat. And we do not increase the size of the circuit that computes G hat, so the size of this circuit stays the same. And this is the encoding. So now if we go back to the obfuscation, if we take this circuit Ci that we constructed and just apply this encoding on the circuit and output all the internal gates of all of these circuits, we get a circuit that we cannot obfuscate by the sample. And this is the idea. Okay, so we have this result, this connection between obfuscation and GapMCSP. We use this connection between GapMCSP to prove a lower bound of obfuscation, but this gives us a path toward proving that obfuscation does not exist, or to prove a stronger lower bounds on obfuscation if we will be able to prove better harness approximation of meta-complexity problems. And I just want to say that if the goal, what you want to prove is a lower bound of obfuscation, it's actually enough to assume that obfuscation exists when you construct the reduction, the level reduction. So you can use, if you want to rule obfuscation, you can use the assumption that the obfuscation exists when you construct the level reduction. And as I said, if you have obfuscation, you have one-way functions, public key encryption, multi-party computation. So you can use any crypto you like, basically, in order to prove this level reduction exists. And actually, there are NP-Completeness result that uses cryptographic assumption in order to prove this NP-Completeness result. These reductions are not level reductions, but maybe it's possible to make them. Good. So to conclude, we showed a connection between GapMCSP and Levin and NP-Completeness of meta-complexity problems and lower bounds on obfuscation. And the last thing I want to say is that we actually, in the end, we got a result which is basically a crypto result. So we use the connection between meta-complexity and crypto to get a result in cryptography that doesn't use meta-complexity at all. This is maybe interesting. And for open questions, so the obvious open questions are, is MCSP NP complete, and are we live in obfuscation? Okay.
Can you say anything about the WIPS encryption? Can you do something similar for WIPS encryption instead of IO? What about that?
Yeah, I think we need,
Yeah, in your proof, yeah.
yeah.
Don't know anything about it. More question? Let's thank you all again. Yeah, we have 10-minute break, and there's one more. There's a reception, but don't be your host. That's okay, that's okay. Going to have okay. We're gonna see.
No, I think if there's